All right, I want to cover some other issues here, and the first one is the expansion of clay soil. We don't talk a lot about expansion, but this is the concept. Dry clay can be thought to be similar to a dry sponge. You've all had a dry sponge sitting by your sink, and you take when you want to use the dry sponge, what do? You put it underneath the faucet and you saturate the sponge, and what happens? It gets bigger. And that is similar to what happens to clay. Acts in the same way. When it goes from dry to wet, it expands. Now, put it this way. If I have a light structure, such as a house is considered pretty light. If it's resting on clay that goes from dry to wet, what can happen? The house can be lifted up. And the lifting is never uniform. So in other words, it doesn't just lift the house straight up out of the ground. In some places, the house may be lifted a lot. In others, it may be lifted only a little. So what happens is that you can get cracking and unleveling and all sorts of problems in the house. Now, heavy structures like 20-story buildings, but they're too heavy to be lifted by clay that is getting wetter. And so we're usually not concerned with expansive clays for such structures as those. It's mostly these light structures like houses that we're concerned about expansive clay. Now, there's one other aspect of, wetting a dry sponge. It gets bigger, yes, but what else happens to it? It gets softer. So envision a filled coffee cup on top of a dry sponge, okay? If we wet the sponge, the coffee cup will sink because the wet sponge is softer than the dry sponge. So heavy structures on top of clays that go from dry to wet can sink. So that could be a problem with a 20-story building. It's an issue, but generally the foundation for a 20-story building will go deep into the ground where soils will not be subjected to wetting and drying. So whereas structures such as houses and things often have shallow foundations, and when they're subject to wetting and drying, those topsoils, if they have a shallow foundation, those topsoils will have changes in water content. But it is something, no matter what, if you have a clay that goes from wet to dry in a heavy building from dry to wet and a heavy building with a shallow foundation, yes, it could sink. Now, pardon me, which clays are the worst? Now, not all clays do this, and it's been found that a high plasticity index generally indicates clays that are more expansive than others. And if you have a low PI, plasticity index, that is generally indicative of the clay not being expansive. If we have a clay that is expansive, there are different things that can be done. I'll talk about it. You can chemically treat the soil. You can get the soil wet before any construction. That sometimes helps. And you can also remove it. In addition, we have some things here going into more detail, chemically treating the soil. Lime is what is often used to treat the soil to reduce expansion. What do? Lime, you mix the lime with the soil and sort of grind it up and mix it and put it back down. So You can mix it in, and there's some other things that you have to deal with the pH, but I'm not going to go into those details. But there are also proprietary chemicals that can be used, and anyway, there are different things that can be. Oh, here, and before I forget, the degree of expansion here very high. Well, it could be for a PI greater than 35. These are estimates. This is just rough, but this sort of thing can be used on the exam to see what is the expansion potential for these types of soils. Like I said, we could add water to the soil before the structure is built, and then take steps to prevent future drying, for instance. And then you can remove the expansive soil and replace it with non-expansive soil. For instance, remove clay, put in sand, something like that. This can be expensive. There are other things that can be done, putting your foundation deep into the ground, and actually for the purpose of, put your house on piles, which is not unusual. If you get your piles down about 10 feet, or 12 feet maybe, or depending on the situation, as long as the pile gets deep into the ground, if the soil tries to swell, the house won't lift up because the piles won't pull out of the ground. You have to put the piles deep enough in the ground so they don't pull out. Okay, the next topic I want to cover is permeability. Now we've talked about this in the past. The simplest permeability test, for instance, is one where we have soil in a pipe, basically. So I've got soil here, and I have a water level at one end. I have a lower water level at another end, and we put water into this end, and the water flows through the soil up here and out, and this is called a constant head permeability test. Constant head, why? Because I maintain this water level here, maintain that water level there, so that the head does not change. We have a constant head, which is H or delta H, depending on the terminology. And what we're going to do is we're going to measure the volume and time of the water that comes through. Now, if you remember, Q equals V times A, that's our pipe flow, where Q is the flow, cubic feet per second. V is the velocity, for instance, in feet per second. A is the cross-sectional area of the pipe. The cross-sectional area of the pipe in square feet, for instance. Now, notice the expression for soils is somewhat similar. We have small q, K times I, which is our V, and A, and they're similar in the sense that Q is the flow in cubic feet per second, for instance. A, again, is the cross-sectional area. What is that? It's the cross-sectional area of this soil. And we can't see the cross-sectional area here because we need a third dimension to see it. So, and K times I is the V, which is, I'm going to call the discharge velocity. And K is the soil permeability, and I is the hydraulic gradient. And the coefficient of permeability, of course, is we measure in the lab, for instance, in doing this kind of test. So this I, the hydraulic gradient, is delta H over L. What is delta H? Delta H is the head drop across the distance L. So it's the difference in head, the difference in head between 2 points. And the 2 points, in this case, there's a point over here and the point over here, over the distance L. So, and in this particular case, the head on this side is what? It's easily seen. It's this water level distance. So, and on this side, it's easily seen. It's also this vertical water level distance. So, we have the head easily defined in this particular test. That's one of the reasons it's easily used. And in this expression, L is the distance between those 2 points. So, like I say, 1 point here, 1 point here. They differ by L, and and then we're looking at the difference in head. So in this case, the difference in head is this delta H, the difference between those 2 water levels. That was the... Now, notice that the hydraulic gradient is dependent on the geometry, not the soil type. It has nothing to do with soil type. In other words, I've just said the soil here, and I haven't said a word about what kind of soil that is. Now, if it's clay, that means what? We're not going to get much flow through it, but we can still do this in clay. If it's gravel, we're going to get a lot of flow through it. So that means we're going to have a big Q if it's gravel. Which means what? If I have a big Q, I'm going to have a big K. The permeability, the coefficient of permeability, K, is a property of the soil. So K is the coefficient of permeability, and it's a soil property. Now, I guess I didn't write that down, did I? So let me just write it down here. K is equal to the coefficient of permeability. And that is a soil property. So we run this test frequently to determine what is the value of K. So what we do is we measure the Q from this, volume and time, cubic feet per second, for instance. And then we know the cross-sectional area of this pipe. We get that. And the hydraulic gradient comes from the delta H here and the L here. So everything in this, when we run the test, everything in this equation is known except the K, and we solve for the K and we get that soil property. Now, something that I didn't cover previously is that there's another kind of velocity that is defined, and that is called the seepage velocity. Now, what is the seepage velocity? If we look closely at what's going on here, so I'm going to look at this pipe. There's my pipe, and when I look at the cross-section of the pipe, what do I see? I see soil particles. So these are all the soil particles. And the water is going perpendicular to this pipe. And what does it mean? Well, where's the water? Where can the water flow? Well, it's got to go around the soil particles. So the actual area that the water flows, so that the water flow cross-sectional area, I'll call it A cross, is less than the cross-sectional area of the pipe, A cross of the pipe, because the soil particles get in the way. So if we want to know what the actual velocity is of the water through that, it's going to be, we have to figure out what is the actual void area. I want to know what's the void area here. And and not use the cross-sectional area of the pipe, but the actual void area. And, you know, the situation, so in other words, if I had a reduced pipe size right there, that would be similar to having the soil particles there. So in other words, if there's no soil and I just have a pipe, what's happening here is I have a certain velocity here and the same velocity here, but when I look at the velocity through the soil, it's actually higher because of this effect of having a reduced cross-sectional area. And you know, this is, sometimes called, sort of like a nozzle. How can we get that? Well, if you remember the definition of porosity, porosity is volume of the voids over the total volume. Now, if I'm just looking at this cross-section here, what I'm going to find instead of volume of the voids, I can say it's the area of the voids. And instead of the total volume, I took the total area, the area of that cross-section, in other words, the area of this whole thing. And so if I take, so I can get the area of the voids, which is what I want, and in other words, I want this area of the voids, not the total area. I can use then the discharge velocity that we previously calculated or used. If I divide it by the n, then I'm going to get my seepage velocity. So, in other words, I will end up with using the area of the voids instead of the total area. So all we have to do is take the discharge velocity divided by n. So I go back to this particular equation, which is V is equal to K times I. I divide it by n, and that will give me the velocity, what's called the seepage velocity, which is the velocity between the soil particles here. Okay, so given that, I want you to do this problem. And it's a constant head permeability test. The cross-sectional area of the entire pipe is 1 square foot. The Q that goes through the pipe and comes out here is 0.2 cubic feet per second. The L here is 2.2 feet. This delta H distance here is 1.2 feet. And using the equations I just showed you, find the discharge velocity, the seepage velocity that I just went through using the N, and the coefficient of permeability of the soil. The value of N is 0.75, and the material is a clean sand. Okay, so pause the video here and give it your best shot to do this problem. Okay, so let's start with the hydraulic gradient. Well, the hydraulic gradient is easy to get. It's simply delta H over L, and we're given both of those. And so I get a hydraulic gradient of 1.2 over 2.2. Notice there are no units here because it's 1.2 feet over 2.2 feet. So the units cancel out. There's no units for I. And then I can solve Q is equal to K times I times A. And the A is here. The I is here. The Q is here. And we can solve for K. We get K is equal to 0.37 feet per second. So that's the soil property. That's a property of this soil. in this condition, of course, if we densify the soil, it's going to have a different permeability. If we loosen the soil, it's going to have a different permeability. But soil in that condition has a K of 0.37. And then our basic discharge velocity is V equals K times I. It comes out to be, so just multiplying this times this, and we get 0.2 feet per second. That's our discharge velocity. To get our seepage velocity, we simply divide by n. So the discharge velocity divided by the n that is given, and we get the discharge velocity of 0.27 feet per second. Notice, of course, seepage velocity of 0.27. Seepage velocity is faster than the discharge velocity, which makes sense because it's a smaller cross-sectional area. Okay, one that I don't talk about in class is the falling head test. What I just went through was the constant head permeability test, but there's also a falling head permeability test. And what's the difference? Well, I can have essentially the same setup, but instead I don't add water here. I just let the water flow out. Well, if I let the water flow out, what's going to happen to this water level? It's going to keep going down. And that's called a falling head test. Now, generally, when we do this test, we have a different test setup. We generally will use a smaller burette, and generally, you know, so that we can monitor this. It's easier to monitor this head drop. It's usually done for soils that are lower permeability, and so we're going to have less flow here. So I have a little tiny burette there, and the water flows where? It goes this way, and then upward through the soil and out, and I'm not going to derive the equation, but this is the equation that governs this test. And if we look at it, we will see that there's a small a. That small a is the inflow burette area. So that's the cross-sectional area of that burette. Big A is the outflow area, which is the cross-sectional area of the soil pipe. And then we have L, which is what? In this case, this is the L, because it goes upward. The flow is like that. So there's the L. The delta T is what? Well, we allow, again, a certain amount of time to pass when we collect this. That's the delta T. We're going to have a certain water level at T equals T1, and then we have another water level at T equals T2. So delta T is T2 minus T1. And then H1 and H2 are what? Well, it's H1 is the difference in head at T1, and H2 is the difference in head at T2. So different, and then what is that? That's coefficient permeability, which is what we're trying to find in general when we run this test. Okay, so do this exercise. For a falling head test, find the K, and here's the given information here. It's a pretty straightforward problem, but do your best to do this. All the information is given. Pause the video here and solve this. Okay, this is just a plug-in, just to get used to the equation. So what do I have? I have A there, big A there, L here, delta T here, H1, H2, and just multiply it out using the natural log. And we get 0.07 centimeters per second. So all this stuff is in centimeters. If you look at the units, you get centimeters per second. It's a common way to express permeability in centimeters per second for some reason, not feet per second. Okay, another topic that we have not yet covered is pumping in wells. Now, what is that? What am I talking about? Let's just say that we have a site that is sand or gravel, because we need sand or gravel to be able to pump out the water. It's an aquifer. It's called an aquifer. So I have a pumping well and I have some observation wells. So we have our water table here. Now, before we started pumping, the water table was there. Okay? So we have a site that we want to extract the water from. The water table is there. I drill a well here and I start pumping the water out. I pump the water out, and what happens? I bring down the water table. So the water table is no longer flat, and I can observe where the water table is by looking at observation wells. And in this particular case, I've got two of them. This is one, and I call this H1. That distance H1, I call this distance H2. And then they're separated from the well. R2 goes to this second well, and R1 is the distance to the first well. And again, I'm not going to derive this equation, but I can get the permeability of this sand or gravel, again, the soil property, by, again, taking the Q, the flow out of the well, and then I have my R2, R1, H2, H1 into the equation like that. Note that R1 is closer to the well than R2, so by our definition, that is, we can't flip those, otherwise we're going to get in trouble with the way this is going to work out. So here's a little exercise. Find the coefficient of permeability. We have a Q here, and notice that I have, this is my pumping well, and here are my observation wells. Now, just pay attention to how we defined R1 and R2 and H1 and H2. So I'm not going to say anything more here. You have all of the information on here, but you have to pay attention to the way that R1 is defined, R2 is defined, H1 is defined, and H2. So look at the picture that we had, and there's enough information in this problem to be able to get these terms and put them into this expression to get the K. Okay, so pause the video here and do this problem. Okay, so I gave you these distances, but what we want are these. And then notice that this is 30 feet, this is 60 feet. R1 is closer, so this is my R1, this is my R2. This is going to be my H1, and this is going to be my H2. So recognizing that, we get H1 is 100 minus 22.3. H2 is 100 minus 18.4. And then R1 is 30 feet, R2 is 60 feet. Then once I recognize that, I take the Q, I put it in here, and I plug everything in, and I get my coefficient of permeability 4.26 times 10 to the minus fourth. In this case, we're working in feet per second. Okay, I should make the comment. This is what we call an unconfined aquifer. I guess I didn't make that point. An unconfined aquifer means exactly what we're showing here. The aquifer is this sand or gravel. That's what we call an aquifer when it's filled with water. It's got to be sand or gravel. We can pump it out. If we have soil that's filled with silt and clay, that's not an aquifer because we can't pump it out. The water doesn't come out very fast, so we don't call that an aquifer. So if I look at this soil profile, I have clay or silt here on the top. Then I have a sand or gravel layer here, and then maybe it's clay, silt, or rock down below, and then I guess I have bedrock here. But notice this is my aquifer because I can't pump water out of this. So the way that this is, so we call this a confined aquifer. Why? Because it's trapped between layers here. So that is a confined aquifer. Now, so again, we have our pumping well here, and we have our observation wells over here, and we can still have the water table up in here. So the water table can still be originally up here. And then we start pumping it, and the water table comes down with time. But let's look at the details here. So suppose I dig a hole like this in this clay or silt. What's going to happen? I'm not going to have any water in this hole. Why? Because the water evaporates faster than it comes into the hole. So I end up, even though the water table is up here, I end up with a dry hole here because the water evaporates very much more quickly than the water comes out of this clay or silt soil because the water doesn't want to come out of those soils. So that's because I don't go all the way down into the aquifer. On the other hand, if I drill a hole down through the clay into the aquifer, then I'm going to be able to observe the water table level because this hole will fill up because it's gone to the aquifer. The water is easily penetrated into the observation well, goes into the observation well, goes up. So I can observe the water table by drilling an observation well into the aquifer. So my observation wells go down into the aquifer, and I'm showing how the well goes to the base of the aquifer. So the aquifer has a thickness of D, and we still have our H2H1, R2, R1, so that is still the same. But now this D works into my equation, and so there's my D there. I get a different equation. There's my permeability, Q, same as before, R2, R1, H2, H1, but now I have my D. And then I got 2 pi, these are not squared, but this is the equation that we use for this one. And we have to note that D has got to be less than H2 and H1, yeah, when I say we don't really change the figure, we're just going to leave it as is here. So in other words, we're not pumping, we're not pumping down to here. We're not pumping like that because then it acts like an unconfined aquifer. So what we're illustrating here is exactly what I've shown. So okay. So this is a confined aquifer. We use this equation for a confined aquifer, which may be on the exam. And I'll stop there.